Hello, welcome everyone to the MPS Talk Series 2021. Welcome in the name of JetBrains and Itemis. For JetBrains, it's obvious, right? They are the developer of MPS. Itemis has been using MPS for 10 years now, I think. Been developing a lot of extensions, and this is why we are co-hosting this event. Although, of course, JetBrains has done all the organization, so you should thank them. My name is Markus Völter. I'm a language engineer, MPS user since about 10 years ago, and I will be your moderator throughout the week. This is the third meetup we've had. We have had two physical ones before, one in Munich and one in Amsterdam. And these were two full-day meetups. This meetup or this talk series, it's obviously not really a meetup, that's why it has a different name, will go on all the week with 2 talks per day, always between 5 and 7 p.m. Central European time. Today, I will give the first talk, so I'm kind of self-moderating. I will change my hat in a moment from moderator to speaker. We're also still figuring out a little bit how all of the streaming stuff works and how the various, the technical person and the moderator and the speaker collaborate, and we might screw this up and then we'll fix it. We have 4 more days to get it right. The second talk today will be by Marcel Riedel. He's an architect at DATEV. And what's really nice is that my first talk will be about KernelF, a functional language implemented in MPS that is like the basis for lots of DSLs people have built. And the second talk by Marcel is, on the one hand side, a really interesting case study of industry scale DSLs, but it's also a case study of using KernelF, so the two fit together. Looks like the people who have organized the program thought about it a bit. So, all right. So you can ask questions in the YouTube chat, and we will answer them after the talk. If the question is urgent in the sense that you need to understand something right now in order to make sense of the rest, then Oscar will interject himself into the presentation and ask me right there. All right, so Oscar, if you want to share the screen, thank you very much. And now I'm switching my hat from moderator to speaker, and I'll give you an introduction to KernelF. KernelF is a functional language. That's what the F means, and it's intended as the kernel of domain-specific languages. That's where the name comes from. I will also talk a little bit about utilities from the Embedder platform that we have used to build KernelF, because the platform is open source. You can use that too. Also, KernelF is open source, so you can also use that. So everything I'm talking about is open source today. Even though I'm giving the talk, it's important to emphasize that the Embedder platform has been developed over a decade now by a whole team, mostly at Itemis. And there, Sasha Lison is the guy who did a lot of the work. Not everything, but a lot of the work. KernelF is kind of my baby. I started it, but again, a couple of Itemis people joined the effort, and so even that is also a team effort. I always like to emphasize that, because it's like one person who gives the presentation, but there's a whole group of people who make all the stuff work. Okay, so DSL development, in our experience, comes in 3 flavors. One is that you extend a domain's general purpose language, like, for example, Java or C, or you have an existing notation in a domain that's already completely defined but not formalized. So you maybe have a bunch of sketching, shapes, and you want to formalize it into a language. But then the most common use case is the development of a new language. And many of these new languages we build turn out to need expressions, functions, integer, booleans, comparison operators, stuff like that. And it's really tedious to develop those over and over again, which is why we've developed KernelF. You can easily reuse that, embed it in your own languages. I'll talk about how to do that, of course. And this saves a lot of work. It's also like driven by this idea where the kind of DSLs we typically build are like a fusion of modeling and programming, where you use high-level domain-specific concepts, various different notations, separations of concerns, domain expert programming, which is all stuff from the modeling domain, right? You can see the dark shades in the left column. But then there is stuff from the programming world as well, things like type systems, low-level algorithms, productivity focused IDEs, which is something we know more from programming rather than from modeling. And the kinds of languages people build with MPS are kind of a fusion of the two. Like you pick the dark parts of, well, the dark colored parts, I should say, from each of the columns to give you the best of both worlds. And again, I hope to be able to illustrate that. Yes, I'm going to hide the cursor. Thank you very much. This was the technical person talking into my ear. All right, so I'll give you a couple of examples of KernelF DSLs first, so you see what you can do. Actually, no. First, going to talk about what the language features are. It's a functional language. There is no state at its core, so it's a pure language, but it does have effect tracking if you need to. It has the usual types, you know, int, boolean, strings, enums, records, collections. It has the usual conditionals, if, the equivalent to the multi-case switch. It has functions, it has blocks, it has error handling in a way that is similar to exceptions, but without the long jump. So it's basically encoding types, errors into types. It has, as I said, immutable collections and higher order functions. And an interesting feature is that it has constraints on all the types and functions. You can have pre and post conditions. You can have invariants on records, and if you will, add some additional declarative semantics to your functional code. There is a funny saying, I think Eric Meyer said that a purely functional language only heats up the processor, because by definition it has no effect. It doesn't do anything. So if you want to write a meaningful program, at some point you cannot be purely functional. And the way we write these languages or these models is that you have a functional core language, which is typically what the domain expert uses to write whatever they want to write. And then you have some kind of runtime driver frameworky kind of thing that, you know, interacts with users, like runtime users, not language users, or, you know, stores data, loads data, and then forwards it to the functional core. And of course, that driver is not functional. It does have state, it modifies state, it interacts with the world. So anyway, so when we talk about what we do with DSLs and with KernelF, it's on this right side in this functional core. There are a couple of features if you really need to manage state. We have boxes, a little bit like Clojure's refs. We have transactional memory, state machines, and something called interactors. I'm not going to explain it. More interestingly, in the functional space, we have a lot of convenient utilities for decision tables that actually use tabular notations. I'll show that. We have temporal types if you need to represent timeline data. We have support for dates and physical units, like you can do. You can annotate, for example, an integer numeric type with, let's say, meters per second as a unit, and then do calculations with that in the type system. Again, now we have the tools. So KernelF comes with a whole bunch of tools. The most important one is the interpreter. So you can run KernelF programs right in the IDE. It also comes with a testing sub-language, if you will. And what you can see here is a test case with a bunch of assertions, and it asserts over KernelF expressions. And as you can see, well, you can't, because I can't run it on my PowerPoint, but you have to believe me that when you press Control-Alt-Enter on one of these assertions or test cases, the program, the KernelF program, is run directly in the IDE, giving you feedback immediately. There's no code generation involved, is what I'm saying. Of course, you can build code generators for KernelF or DSLs built on top of KernelF, but by default, the interpreter is what ships with the language. Gives you a very nice, very quick turnaround. It's actually very convenient. We have coverage measurement. So we can measure both coverage of your subject program based on your test cases, but we can also cover measure coverage over your language definition, both the structure and the semantics definition in the interpreter. This is important when you define a language. You want to know whether your test cases, cover all the corner cases of your language implementation, and you can do that as well. It's very, very helpful if you want to stabilize your language. We have, for debugging, we have a tracer. Since the language is functional, there is no stepping through in that sense, but the tracer gives you a complete snapshot of the complete functional calculation tree, and you can navigate through that here. And you can overlay the values of, if you will, expressions in a given program execution directly over the code. It's like putting the execution values over the syntax. We have a REPL, read, eval, print loop, where you can add or enter expressions and press Ctrl-Alt-Enter, just like the test case, and you get the result immediately. We have a test case generation, where we can automatically generate test cases. This is experimental, as it says in red, very important. This is not as stable as the rest of KernelF, but it's nice to play around with. We also have mutation testing, where you can randomly modify your test subjects, assuming that if your tests cover everything, a random mutation should mean that one test will fail, because now the program is different, and if the test is meaningful, the test will now fail because the program has changed. So nice thing in MPS, you can easily show the original program and what has changed, right? So you can, for example, in line 3 here, you can see that the original code was a multiplied by 1, and you can see the mutator added a +1 to that expression. And obviously, if you have a test for that function doodle, it will now fail. Again, also experimental. So now finally, a couple of example languages that people have built. Again, KernelF is open source, but these languages I'm going to show are mostly built by some of our commercial customers. So here's an example from a language built by Voluntes. It's a French-American, well, I guess no longer really a startup, was at the time more or less, and they have built a language for expressing healthcare applications. Basically, they have expressed algorithms for dosing treatments and for tracking treatments. And there was a state machine underneath it, but then there was also lots of decision trees and decision tables to make decisions about medical situations. And I always make this joke that while we had this project a few years ago, we always used, for some reason, the diarrhea example just right before lunch. And I'm happy to report that it's now more or less dinner time. So it's, again, a really good fit. Here's another example from a language developed by Datev. It's a language for salary calculation, and you will see lots more about this language in the second talk today, as I mentioned. This example here tries to introduce temporal types. Again, the temporal types themselves are in KernelF, but this is a DSL that uses them. In the very last line, you can see a temporal type. It basically says that starting or from January 1, 2017 onwards, that salary thing was 5,000 euros. You can also see the euro unit there. And on May 1, that salary changed to 6,000. So again, you have a temporal value, which is not simply a number, or any other type. It represents the change of that value over time. Now, interestingly, these temporal types come with support for primitive operators. So for example, if you have a temporal value a and a scalar value s, and you add the two, then you get the same time slices, but each of the values in those slices now gets the value s added. If you have two temporal values with different slicings, then the resulting temporal value gives you, if you will, the superset of all slices, and then the respective components are added together. And again, this is built into the interpreter and the type system natively, so you can write down expressions just like any other expressions over primitive types, but behind the scenes, all this temporal calculation is going on. And then you can use this, for example, in these salary calculations. If you look at the third line of the calculate rule here, you can see how there's a multiplication going on that works with temporal types, but it's not visible. Then in this particular language, there is also an interesting thing going on about versions. DATEV needs to express different calculations over time, and we have extended, or we have built a type system for that DSL as an extension of the KernelF type system, which gives you in the IDE a static error if you try to work with incompatible data. So it's basically a type system that knows the versioning of the program, not in Git, but as part of the model itself. It was very interesting to build, actually. Here is another DSL. It's the same customer. Well, it's a different department of that same customer. This is the text calculation people at DATEV. They use a completely different DSL that also uses KernelF for calculating, basically for expressing all of German tax law. You can probably imagine that this is going to be a huge program in the end, because German tax laws are large and complicated and strange. The way you write down the calculation logic is basically a big tree, where the value, for example, this tax in the third line from the bottom is the sum of these income tax and the church tax. You can see that the church tax makes a distinction of whether you're currently in the church or not. And then the total tax sums up your monthly taxes, and then, that's what you pay. On the right side of the screen, you can see a test case. In this test, we also represent the calculation as this tree, and then you can supply data, like, for example, the 5,000 in the gross line is a value is input data, and then those fields with the question marks, these are assertions. And again, you can run these tests right in the IDE, and you get the little OK thingy shown on your assertions. As a little side remark, let me just mention that if you find all of this fascinating, DATEV are hiring MPS people. So if you're interested, you can ping me or ping DATEV directly. So how do we use KernelF, right? So here is the way I do that. I start most of my customer projects with KernelF because it has a lot of stuff. I can start, writing code in MPS that runs immediately. But of course, it's boring functional code. So right after that, I start to build domain-specific abstractions around the KernelF functional core. For example, this tree that we've seen in this last of the examples, that's obviously something we've built specifically for DATEV, and this tree thing is not part of KernelF. So we start with these declarative domain-specific abstractions and embed KernelF. And I'll give you an example how technically to embed KernelF after this thing here. So then we notice some functions are missing in KernelF, or some types are missing. We just add those. And we notice that some things are too complicated for the domain users. For example, higher order functions on collections are not something that an average non-programmer domain expert will understand. So we just use MPS constraints to throw these out and add something that is a little bit more convenient. For example, just going back here, if you look at this Summe thing on the middle of the screen, left side middle, Summe is German for, you guessed it, for sum. So it's basically a higher order function that sums up all the entries in this monthly salary collection. And you could write this with a KernelF higher order function, but this is more easy to read and more domain specific. So that's what we've replaced the default with. You will also notice that some things in KernelF you just don't need. You don't want to replace them with something else. You just don't need it. For example, many people don't want support for option types. Again, because that's something that is not necessarily intuitive for domain users. And honestly, if I ever create a version 2 of KernelF that is not compatible with what's there now, I would remove option types, because although it's nice from a software engineering perspective, nobody cares. I wouldn't do it again. So, and then we iterate, right? So we add a little bit more, we replace a little bit more, we remove a little bit more, and we do a little bit more of the removal and the adding and the replacement. And so that's how we develop DSLs. We start with I just read one of the comments, I'm sorry. We start with KernelF, build specific stuff around it, and then we cut down KernelF to what we need. All right, so I'll give you a few pointers of where and how you do the extension and stuff, and then I'll give you a concrete code example of how to do it. So the first important thing is that KernelF itself is not one language in terms of MPS. It's a collection of 15 languages maybe, and you can pick and choose, right? If you don't need the REPL, well, then your dev kit just doesn't use the REPL. If you don't need collections, well, then you just don't include the collections part. So there's this like coarse-grained way of deciding which parts of KernelF you want and which you don't want. So that's your first level of like customization. Then there are a whole couple of abstract concepts that are built specifically to be extended. The obvious one is expression, right? Because in KernelF, more or less everything is an expression, except for those things that are types, top-level contents, or dot targets. So types is also clear. Things like integer, records, these are types. Top-level content is an interface that you have to implement if you want to put something on top level, like at the very top level in a KernelF library or test case. Again, I'll give you examples of all of those in a few minutes. And the interface I.target is what you use if you want to do like something .blah, and your blah has to implement I.target. How do you remove things? MPS has these can be parent, can be ancestor constraints, and so you can basically say, within this part of my domain-specific program or of my DSL, I do not want to allow this part of KernelF. And because of MPS being a projectional editor, the user experience of actually not having something in the language and constraining it out with a constraint is identical. So for the user, it's gone. And so this is why you can have, if you will, negative variability. You can remove things that are already there, and for the user, there's no distinction between, removing stuff and never having had it. It's very nice. KernelF also has an exchangeable set of primitives. As I said, and it comes with ints, booleans, strings, reals, stuff like that. But if you want your own completely different set of primitive types, you can replace them. This is actually not so simple, because think about an if expression, like if x greater than 7, then blah, else blub. The type of that condition is Boolean. And so for type checking, you need to know in the language implementation what the language's Boolean type is. And so if you want to use your own Boolean types, I have to be able to plug that into the language implementation. And that's what KernelF supports. Yeah, also, there are a couple of things for which we have interfaces. For example, there's lots of different domain-specific things that have members, like looks like a record, but has a completely different syntax, maybe a different construction syntax also. And so that's why there are interfaces for these things. So you can have your own domain-specific construction, but it still uses the iRecord type and iMember interfaces so that path expressions work automatically. And of course, if you don't like the syntax, the concrete syntax, you can always override the editor. That's just default MPS behavior. So I want to run through an actual language extension example and to give you an impression of how this works. And of course, I'm not very creative regarding coming up with example languages, right? When I need to come up with an example language, it's always the state machine language, because everybody knows how state machines work. So we see a state machine top left. It's called traffic light, the obvious example for state machines. It has one event, button pressed, and it has 3 states. And basically, when you're in the green state and you press the button and some condition holds, then you go to the red state. And if some other condition holds, you go to the end state. And you can press the button again, and you jump between red and green until you go to end. And you can, and of course, this is a DSL, right? So obviously, I have defined this language extension myself in MPS. And I can now instantiate that state machine with this create expression. And I can then use that value m, which is obviously m for my state machine. I can use that variable m down there in my test and basically run the state machine and assert that it behaves correctly. So let's see how this works. So obviously, the state machine itself, since it lives inside, I didn't show that, but it can live inside what we call a library. A library is just the default KernelF thing where you can declare variables and constants and records and all of these high-level, top-level things. And the state machine can live right along that. And how do you do that? Well, simply you implement top-level expression content. If you implement an interface, you can use state machines or your concept at the same place where you declare records or functions or something like that. Now let's move on. How do you make the state machine something that can be used as a type? Well, you create a concept state machine type that extends type, right? Type is a concept from KernelF that is used as types. Like, for example, integer extends type as well. Record type extends type, and your state machine type extends type, and it refers to the machine of which it is a type, right? It's the same pattern that, for example, base language uses to have class types, right? I think it's called classifier type. It's something that extends type and points to the thing of which it is a type. In this case, state machine type is a type of state machine declarations, and so that's exactly what this represents. How do you do this condition here? Well, there is the guard concept. Guard is something that is specific to this example language here, and it has one child of type expression. And because everything kind of in KernelF is an expression, if it's not the type or top-level content, you can write anything like 5 + 7 times my record dot blah or foo, meinte. And you can, any valid KernelF expression is structurally valid now here inside a guard. Of course, the A is a little bit special because the A is actually a reference to one of these attributes. And so how do you make that work? Well, you implement an expression that is in this case called attrref, attribute reference, that points to the attribute. And again, to make it plug-inable in expressions, you simply extend expression. And then you need to do a little bit of scoping to see the right attributes. And finally, to be able to say state machine instance dot is in state, you build something that implements I.target. As I said, I.target is the thing that lives on the right side of dots. And you can see that the is in state op implements I.target, so it can be used on the right side of well, technically it can be used on the right side of a dot, but anything can be on the left, right? But you only on the left, right? But you only want to allow it, if you will, as an operation on a state machine. So you have to add a constraint. In this case, it's a can be child constraint, and it says that you can only use the is_in_state thing if the parent node, which is always a dot expression, because dot targets only live in dot expressions, is of type state machine type, right? And so this way you can make sure that if you press Control space after a dot, you can only see the is_in_state thing if on the left of the dot you have an expression that is of type state machine. So talking about types, how does this work? Well, first thing, we said that the condition in this guard thing needs to be Boolean. Actually, we haven't said that yet, but it's obvious, right? It needs to be a condition, and conditions are Boolean. So how do you do that? Well, you add a type system rule to your guard that says, the condition member of guard needs to be, and now this ptf.create Boolean type. PTF is the primitive type factory. That's where you plug into KernelF's pluggable type system. And this one expresses that whatever structure the expression in the condition has, it needs to be of Boolean type. Second example, the attribute reference, right? What's the type of the attribute reference? Well, it's the type of the referenced attribute. So you simply write one of these inference rules, and well, now your A is of type integer, and problem solved, type checking works. And finally, for the is_in_state operation, you know that is_in_state should return true if the machine currently is in the state you pass in. So again, you define that the type of the is_in_state operation is another Boolean. So that is structure and type system. I don't discuss editors because editors are just MPS. But we should briefly look at how you integrate all of this stuff in the interpreter to make it run. So the first thing you need to understand is that the execution domain of KernelF is Java. So this means that the code you write to define the behavior of KernelF stuff is Java code. This also means that the interpreter operates with Java values while executing the language. So this means that in order to execute a state machine, we need some kind of Java object class that represents the runtime state of state machines. And that's what we see here. There's a class state machine value. It points to the machine. It is a value of. It has a member for the current state, and it has a map for the attribute values, because if you go back here, you can see that you can define attributes in your state machine, and you can assign values. And obviously, we need to then store these somewhere. We have a constructor for a new state machine value, and we have another constructor that takes an existing state machine value and the new state in which you want the state machine to be now. Remember that KernelF is a functional language, so all values are immutable. That means if you go from one state to another in your state machine, the current state machine value can't change. You have to create a new value that has the same attribute values, but then has a new current state. So that's what the second constructor does. And then there's a bunch of getters and setters to, set attribute values, and, it's not interesting. So then how do you plug this into the interpreter? So the interpreter is expressed in a DSL for specifying interpreters. I'll talk about that later when I cover the embedder platform. This is an extension of MPS that we've built at Itemis, and that is, well, intended to efficiently and concisely build interpreters for your language. And so what you can see on the left here, this create, that is the, I'm gonna just briefly scroll back. That is the, is the create expression here, where you create a new instance of the state machine you pass in as the argument. It's like you create a new state machine instance of traffic light that is in its initial state. So what you can see exactly that happening on the right. You create a new state machine value object, right? The class that we just created or that we just saw. You pass in the type of which it is the instance. Then you go through all the attributes defined in your machine, and you call the setter for the attribute. And now what this hash thing does, this hash parents a dot initial value, it evaluates, it calls the interpreter recursively for the expression in initial value of the attribute. So interpreters typically work by recursively invoking the interpreter again for different nodes. And this hash thing is syntactic shortcut to invoke the interpreter. We have made it very short because you do it all the time in an interpreter implementation, because that's what an interpreter does. So again, we create a new state machine value, we iterate over all the attributes, we calculate the value for each of these attributes, and we call the setter, and then we return that newly created state machine. Now, what happens if we call trigger? Trigger means we pass in the event, and then we want the state machine to react, right? It needs to evaluate check which transitions there are for the event, and then evaluate guard conditions and so on. So let's look exactly what's going on. There is this for each thing that goes through all the transitions of the current state, right? Then it checks if that condition, if that transition is triggered by the event that is mentioned in the trigger operation. That's what the first if does. If we find one, so if the event in the transition is the same as the one that's currently being triggered, then we check if there is no guard condition, we continue. And alternatively, if there is a guard condition and evaluating that guard condition equals to true, then we create a new state machine value for the target state of that transition. And we run the setters that are associated with the transition, and we return it. Now, there's one more detail to explain. If we go back here, we can see that both in these conditions and in these setters, we can refer to attributes of the currently executing machine, right? So this means that in the attribute, as part of the execution of the guard, like the hash t.guard.condition, you should see my cursor now, I guess, here, we might encounter an attribute reference, and so we jump here. So how do we communicate from here to there what the current machine is that we're iterating over? And we do that with the environment. So before we execute any of these transitions, we put the currently executing machine that we have gotten from the left side of our dot, we put that into the environment under this key. And then here in the attribute reference, we can pull out that currently executing machine from the environment. And then we can ask it for the value of the attribute we're referencing. So this env thing, that is something that is part of the interpreter language. It's something you will find in every interpreter framework. That's just how interpreters work. We use it for all kinds of data passage, right? So here we pass the current machine, but also if you are in a dot target, so if you're on the right side of a dot expression, you need to get to the value that is on the left, right? And so the way this works is that the interpreter for dot expression first evaluates the left side, puts the left side into the environment under this key, and then calls the evaluator for the right side. And that's when we end up here. So we can then grab the result of the evaluation of the left side from the environment. All right, so this was a very quick run through. through a KernelF example language. I realize also from the comments that I can kind of glimpse at with one eye that not everybody has understood everything. That's obvious, right? This was not intended as a KernelF tutorial. This was intended to show you that if you know MPS and if you orientated yourself around KernelF a little bit, it's really easy to build these extensions usually. And you simply inherit from a couple of things, and even the interpreter is just whatever this is, 20 lines of code to get the thing to work. So my intention was to give you a heads up of how to approach this. This was not intended as a detailed tutorial. All right, so this brings me to the last part of my talk. I just very briefly want to point you to features of the Embedder platform that might be interesting for you. So the Embedder platform is a bunch of MPS extensions. KernelF uses them, but they are not specific to KernelF, and your language can use them too, right? These have been developed by various people, mostly Itemis folks, sometimes financed by some of our customers or co-financed, but there are other contributors as well. This stuff lives in partially the MPS Extensions repository that is by default, I think, registered in MPS, and other things can be downloaded in a place I'll give you at the very end. So, grammar cells. This is the most important thing, in my humble opinion, that you need to know when using MPS, apart from MPS itself. It's not so easy to build editors in MPS that behave nicely. Like if you have a textual notation, you want it to behave more or less like a text editor and not like, like a projectional editor. And grammar cells let you do that. They allow you for linear expression editing. You can set parentheses and it automatically shuffles the expression tree. You can do flags, things like public class. You can, you go in front of the class, you type the public, or you press backspace on the public and it goes away. It would be a complete separate talk to explain this. I just want to point you to this. Get grammar cells, read the paper. If you Google grammar cells, you'll find it. It's a life, in my opinion, it's a life changer for defining MPS editors if you want nicely behaving textual notations. The platform also comes with notations for tables. You've seen some examples in my KernelF presentation. Here is a random collection of others. Yes, the cursor, thank you. Thank you, technical person in the background. You can see, tables always look like tables, right? But having this available as an abstraction, as an editor abstraction to include in your own language is also very useful. We have also notational primitives for math symbology, things like big sum or big product, fraction bar, various parenthesizations, vertical layout. Again, here you can see a use of this notation in Embedder C. So we have built a C extension that uses mathematical notation, but we also have a KernelF extension that has mathematical notations. These are two different languages because they extend different base languages, but they use the same editor foundations for defining the math notation itself. So, and this math notation that you use for defining your syntax for your own language, that's part of the platform. The platform also comes with a diagram notation, so you can build full graphical drag and drop, line drawing, context menu, palette on the right, drag and drop graphical editors. Inside those graphical editors, you can still embed the normal MPS cell-based textual projectional editors, so you can have code completion of your expressions in the graphical box. It doesn't work completely seamlessly because of various details, but it works reasonably well. It's actually really cool. All right, so next one, rich text. this is a way of working with semi-structured content, which means you have fundamentally unstructured text, like in a normal text editor without any projection magic and stuff like that. But inside this flowing text, you can press Control Space and instantiate MPS nodes. And this way, you can have, for example, I don't know, some documentation text with, for example, here, references to figures or references to listings or anything else. You can obviously build your own kind of node that you plug in here. And then you have a mix of just plain text and embedded nodes. Very, very nice. We have a plant UML integration where you can very easily create read-only. So it's not a graphical editing framework. You've seen that before. This is just rendering graphical diagrams with the well-known plant UML. And it has go to source support. So you can click on stuff and then it opens up the MPS editor. Very nice to give you graphical overviews of textually modeled stuff. We use this actually much more often than the graphical editors because, you know, building graphical editors is quite a bit of work, even with the frameworks, especially if you want good usability, because there's just so many different kind of gestures people want and stuff. It's usually just better to use a textual or tabular or something like that editor and then render the pictures and have click to go to source support. We have a DSL for building custom project views, right? This standard MPS project view can be replaced with your own, with custom actions, custom icons, custom structure. This is also very nice if you want to build, well, custom IDEs. They don't just rely on custom languages, but also on custom buttons and custom project views. We have assessments. Assessments are, how do we explain that? These are basically queries over your model that you can define, and they can be used, for example, for code smell detection. Like in this case, we say that in this text language, there is a node that is marked as public, but it's unnecessarily public because nobody uses it. So it's a code smell, and you can fix that. And this gives you a list of these, and you can explicitly update this is committed along with your source code. So it's like a living kind of assessment or an audit that lives along your code, and you can update it whenever you want. And you can then, it then shows you the delta even, so you know what has changed in the last update. And finally, I think that's the last one, query lists. Normally in MPS, the location where a node is projected is always its physical location in the syntax tree. But sometimes you want to show stuff in other places. Like if you look on in the example on the right here, there is this is a DSL for defining UIs, and here is a widget, a field definition that refers to a data item. And here you can see the list of validations that apply to this field. Now, these validations are defined in another place. They refer to the field in the data. And so here we run a query over the syntax tree that says, give me, you know, all the validation rules that apply to the field of which, that apply to the data field of which this widget is a graphical representation. And then we show them here, and control click jumps to its definition. Oh yes, and of course the interpreter. You've seen that, right? You define these Java-based evaluators. You can use the language concept here. You can specify constraints on the types of the children, if it has any, and then you implement the actual logic in Java. All right, so we actually have time for questions. That's great. That's all I had to show. The last slide shows the URL where you can get all of this. If you go there, you you can download KernelF and all the dependencies from the platform. Okay, so I'm going to stop my screen share, stop screen. And we can discuss questions. So, anybody has questions? I think the idea is that you type them into YouTube, and Oscar is going to read them.
Hi, Markus. Well,
Hi, Oscar.
first of all, thank you very much for the talk. Well, I was just going to introduce a little bit myself. I'm Oscar. I'm the product marketing manager of MPS, and right now I will be working as the reader of the questions. So we have a few minutes. So, Markus, I think you already answered most of the questions, but how about if we go through them?
Yep.
Okay. Okay, I think I can even show the question here. Okay, yeah. Zrin is asking, how hard is to add a new addition to KernelF without breaking what has been done? And what is your methodology in terms of software engineering?
Well, I think I gave an example of how it is to add to KernelF. It's not hard, right? In my opinion. And obviously you have to, learn the language a little bit and go through a couple of examples. But I think this question was probably asked before I showed the demo. So I think I answered it.
Okay, yeah. Well, I think you also answered this one, but I was just wondering, well, they're asking that there's a beginning course of KernelF. You mentioned, I think you mentioned no, right? Or is there any kind of...
Actually, there is a tutorial. The problem is it's on an old version of MPS, and somebody has to do the migration. Maybe as a volunteer in the audience here. So there is 2 or 3 papers I wrote around it that give some hints or explanations of how to extend and how to use it. And there is the explicit tutorial, which is outdated, which somebody has to fix. And of course, there is the this particular example. I uploaded that to YouTube as well. Sorry, to Git as well, GitHub. I can post a bunch of links later into the chat during the other talk when I have my hands free.
Okay. There's another question. This is recent. Is there any documentation on using the tables editor UI features?
Yeah, I mean, documentation, it's always this thing in open source software, right? It's there, but it's not great. And it's, I would say there's lots of examples where you can, just press Ctrl+Shift+S, jump to the definition of the table and look how it's done. I don't think there is a systematic tutorial, unfortunately. Again, maybe there is somebody in the audience who wants to help with that. That would be really appreciated.
There's one question from Noli. How many developers are focused on working with MPS extensions right now?
You mean developing them?
I think mine.
Yeah, of course you can't know. It's not your question. Yeah, I don't know. So there's 3 or 4 people at Itemis who regularly fix things. Right now, there is not a lot of fundamental extensions. In fact, we're trying to throw out stuff that is not stable enough. So I gave you in my presentation maybe the 10 most stable and most important embedded platform features. But there is probably 50 others, and 40 of them are crap. And we're working on cleaning that up. And various people involved at JetBrains and at Itemis.
There's one more from Federico. What is iets3 stands for?
Yeah, so we have developed the original version of KernelF in a government-funded research project. And the project was called IETS3, and I think it stood for Integrated Engineering Tool for Systems Engineering or something or other. I think I even came up with a stupid name, but I forget. So it's like, now it doesn't mean anything. It just means IETS3. It's a stupid namespace, and that's it.
Okay, fair enough. There's one more of Mikiel. I was already answering on the comments, but maybe you can add something. I assume you can generate code from KernelF. This is probably Java. Is it easy to replace that to another language?
Well, actually, yes to all of them. We have a Java generator for KernelF, and I'm embarrassed to say I'm not sure if it's open source or not. Maybe Vladi, colleague at Itemis, who is in the audience, can type something. I really don't remember. I'm sorry. We have developed a KernelF to C generator, a customer project, which is not open source, and there is the starting point of a KernelF to TypeScript generator as well. So yes, it's easy to replace because the Java generator is not structurally part of the KernelF languages. It lives in separate MPS languages. So if you just don't use those, and then it has no generator, and you can build your own generator.
Okay, we have one more from Paul. So you say graphical was hard. Is there any graphical swing-based language that you think works well?
Like inside MPS or generally? I'm not so sure I know what this question means.
I'm not really sure either.
Maybe Paul, you can clarify. And yes, it would be a good idea to remove the IATS3 namespace and rename it to KernelF. But two problems: one, there is other stuff that is also IATS3 but not KernelF, and B, it's work. And especially renaming things, languages in MPS is sometimes not quite as seamless as you might perhaps maybe want. And so we're working on it. We want also to have a separate distribution that only has KernelF and not the other crap. And at that point, we will rename it as well. It's not a big deal, right? It's just a namespace.
Okay. Robert is asking, do you have used KernelF in less calculation-heavy domains? I wonder if the function expression-heavy way of thinking works well with the domain experts that have a different background.
Well, I don't know, because I have honestly not met any interesting DSL that does not have at least simple arithmetic expressions or comparisons. So even if you have the stupid recipe DSL example, you want to be able to express that, you know, I don't know, some condition. If it's more than 5 people, then use 7x, otherwise use 2x or whatever. So we have different customers in which we use different subsets of KernelF. Some use everything and add to it. Some use almost nothing, only the primitive types and a couple of basic operators. But if you don't even have the basic operators, then you just don't use KernelF. I mean, if you have no use for expressions and primitive types and function stuff, then just don't use it.
Well, there's somebody asking if you can share the URL again, please.
Yes, I will paste a whole bunch of URLs in a few minutes once Marcel has started talking.
Okay. I think there's no more questions for you. Do you see something?
Well, I don't know what of those has been answered by Vladi. Maybe we should give people. Okay, Paul. Yes. So I have. So the graphical diagramming language that we have built is, in my opinion, the best graphical editing framework in MPS, right? There's not so many alternatives, right? So it's a kind of a trivial statement. But if you compare that with a modern, for example, web-based graphical editor, you will run into a couple of quirks. It's not like bad, but the effort to build it and the usability, in my opinion, the sweet spot is textual modeling or symbolic table-based modeling and rendering pictures. It's less work. It's just less pain all around.